Hello, everyone. This is the Chapter 11 lecture for this week. So, hopefully this one should be pretty simple because it is basically just the same material that we covered in the momentum lecture. It's just with a new with angular momentum instead of linear momentum. So in the same way that all of the angular stuff that you learned last week was analogous to the linear things that you had learned before, angular momentum is just going to be analogous to linear momentum. So instead of mv, it's I omega. uh it's still conserved if there or and instead of being conservative, there's no force. It's conservative, there's no torque. So, first thing we're going to do, the first section that we're going to do is going to be rolling without slipping. So, what is the definition of rolling without slipping? Rolling without slipping is means that us a ball or a wheel or any material rolls down, rolls across the street, rolls down a hill, anything like that. Then if it's not slipping, uh, then at the bottom, at this point P, there is going to be zero velocity. It's going to be standing completely still because it's not moving forward, it's not moving back, it's just moving uh, around the circle and then forward with the center of mass. So if it were slipping, then it would have a net velocity at that point P, but there is no net velocity, therefore it's rolling without slipping. So since it's rolling without slipping, the force of friction that we're going to deal with is called static friction, or is static friction. And instead of pointing to the right, like it does in the book, I'm have it pointing to the left because that's going to be what is going to cause a torque, allowing it to move in the same direction as V center of mass. And it also is just uh, pointing to the left is what gives us the answer. It's what's going to be able to give us the answer in a little bit. And I uh, went through a lot of different Google results to make sure that I was right. About half of them said I was right, about half of them said I was wrong. But in order to get the answers that we're going to get in a few minutes, they had to have it pointing to the left instead of the right. So if it's rolling without friction, then what is the angular velocity omega with respect to the normal velocity? So at point P, the point that doesn't have any velocity with respect to the ground or respect to the center of mass, uh, is going to have V center of mass, the motion of the center of mass moving to the right, minus R omega, which is the motion pushing it around in a circle. So this is equal to 0. So V center of mass is equal to R omega, or omega is equal to V center of mass. Okay, divided by R, where R is the radius of the sphere of the disk. Whatever is rotating, it's the radius from the center of mass to the point where it to the point where it's rotating. So if it's rolling without slipping, then omega is going to be equal to v center mass divided by r. And then alpha is d omega dt is going to be uh, d v center mass over r dt, which because r is a constant is just going to be 1 over r d v center mass dt equals 1 over r alpha, or 1 over r acceleration of the center of mass. And then similarly, you do the same thing in reverse in order to find theta is equal to distance covered by the center of mass divided by r. So hopefully that should make sense. This is not going to be super in-depth, or this isn't going to take super long. So basically the main takeaways we got are that omega equals v center mass over r, alpha equals a center mass over r, and theta, the angle that's been subtended, is equal to the distance that's moved divided by r. So we're just going to quickly do a problem with this, just because it is a useful formula to know. So if you have a ball rolling without slipping down a hill, then friction is going to be pointing this way, gravity is pointing this way, and normal force is pointing this way. So mass, okay, jeez, Louise. Times the acceleration through the center of mass. So the acceleration, so when I say acceleration through the center of mass, or v center of mass, then that's just going to be the type of acceleration or velocity we were talking about with normal uh physics problems, with normal mechanical problems, kinematics, stuff like that, because the velocity moves through the center of mass, or it moves with respect to the center of mass, then the A is just going to be A center mass, V is going to be V center mass. It's always going to be the same thing. We're just including center of mass here because we also have that additional velocity for a particle that's moving because it's rolling. So this is just the linear acceleration, which, if you think about it, makes sense because the acceleration through the center of mass is going to be the only part that's not rolling in this case. So this is all for rotation around the center of mass. So this is going to be equal to mg sine theta minus fs. And then the torque equals I alpha is just going to be F static times R, because F static, or sine of 90, is just going to be F static R, because the frictional force is the only force that's going to be pointing in any direction other than along through the center of mass along the radius. So normal force points through the center of mass along the radius, and then weight force points from the center of mass down through the radius towards the center of the Earth. So the torque is the only one is only going to be caused by Fs, and then Fs R is going to be equal to the magnitude of the torque. So Fs is equal to I center of mass alpha divided by R is equal to I center of mass A center of mass divided by R squared, or A center of mass divided by R divided by R. So this is going to be A center of mass times I center of mass, the angular or the moment of inertia, divided by R squared. So M A center mass is equal to mg sine theta minus I center mass over R squared times A center of mass. So A center of mass, the acceleration through the center of mass, times m plus I center mass over R squared is equal to mg sine theta. So A center mass is equal to mg sine theta divided by m plus I center mass over R squared. So this is going to give us the acceleration. If we're rolling without slipping, this is going to give us the acceleration through the center of mass or of the object. So instead of it just being g sine theta, it's going to be mg sine theta divided by m plus this extra term, I center mass over R squared, which is going to slow it down, because in addition to moving the particles linearly, the gravity and friction also has to gravity and friction also have to move the whatchamacallums, have to move uh the movement of the, so there's going to be static friction, which is going to lower the acceleration through the center of mass, and then that static friction is going to be moving the particles in a circle. So that's where you get your I center mass over R squared. And then one thing that you should also note is that Fs is less than or equal to mu s times n is less than or equal to mu s times mg cosine theta. I'm not deriving these forms for like mg sine theta, mg cosine theta anymore because we've done this a dozen times. But first is less than or equal to mg cosine theta. So A center mass, I center mass over r squared is less than or equal to mu s mg cosine theta. So mg sine theta times I center mass over r squared times m plus I center mass over r squared is less than or equal to mu s m time mg cosine theta. So mg gets canceled out. I center mass over r squared. So sine theta times r squared over I center mass times m plus 1, I believe. No, that doesn't make sense. Sorry. Yeah. So times 1 over m times r squared over I center mass plus 1 is less than or equal to mu s cosine theta. So tangent of theta is less than or equal to mu s times 1 plus mr squared over I center of mass, which is similar again to the critical angle formula that we derived a while ago, but has this extra term mr squared over I center of mass. So, uh, yeah, we derived that a while ago, and it was also a problem on your last exam. So tangent theta for a block that's sliding is just less than or equal to mu s. But in this case, it's less than or equal to mu s times 1 plus mr squared divided by I center mass. Okay, so that's all I have to say about rolling without sliding. I'm going to come back with a section about uh, movement, uh, about conservation of angular momentum, about what angular momentum is and what it means to be conserved. Okay, yeah. See you after the break.